In this problem, we study the three-dimensional pallet and case packing problem. The goal is to arrange items of different sizes inside three-dimensional bins or pallets, while minimizing wasted space and reducing the number of containers used. In real distribution operations, packing quality directly changes transportation cost, container count, and warehouse throughput. Even a 1% improvement can scale to very large annual savings when you ship thousands of orders per day. Three-dimensional packing is computationally difficult because geometry creates many interacting constraints. Every item position affects what other items can do, and small changes can break feasibility. This is why the problem is considered NP hard in practice. As the number of items grows, the number of possible arrangements grows extremely fast, so we rely on a structured toolbox rather than brute force. Imagine a major e-commerce distribution center processing thousands of orders each day. Items range from tiny electronic components, as small as 2 by 3 by 1 centimeters, to large household appliances, as large as 60 by 40 by 30 centimeters. The facility must pack these heterogeneous items into standard containers while keeping the pack stable, safe to handle, and efficient to ship. The operational impact is not just space usage, but also labor efficiency and damage prevention. Packing is not only about volume. Structural stability matters because unsafe stacks can collapse during handling. Weight distribution matters because concentrated loads can crush items or damage pallets. Fragility protection matters because some items must be isolated from pressure, and accessibility matters because workers need to unload and pick without excessive rehandling. These practical rules are why real packing is harder than pure geometry. This chapter uses a tier structure. Tier 1 builds the mathematical mixed integer programming formulation. Tier 2 uses iterated local search with perturbation. Tier 3 uses a BAT algorithm inspired by echolocation. Tier 4 uses meta-learning, so the method can adapt across instance types. Tier 5 integrates a digital twin. Tier 9 introduces quantum optimization using a quadratic binary formulation. Tier 11 explores programmable matter as a future physical cyber transformation. Tier 1 is the rigorous baseline. We decide which bin each item goes into, and we choose the three-dimensional coordinates where it is placed. Feasibility requires two things. Items cannot overlap, and every item must stay inside the bin boundaries. The objective minimizes the number of used bins and also includes a height-related penalty that discourages tall stacking when possible. This slide defines the sets and parameters. Items are indexed as a set of items to be packed, and bins are indexed as a set of available bins or pallets. Each item has length, width, and height. Each bin has its own length, width, and height. A large constant is used in big M constraints to switch geometric constraints on and off, depending on whether two items share the same bin. The decision variables include a binary assignment variable that indicates whether item I is placed in bin B. There is also a binary variable that indicates whether bin B is used at all. To represent geometry, we use continuous position coordinates for the bottom left corner of each item in 3 dimensions. We also use ordering variables between item pairs to express non-overlap along at least one axis. The objective has 2 parts. First, it minimizes the number of bins used. This directly targets reducing containers and shipments. Second, it adds a height penalty term that discourages tall stacking by penalizing unused height above placed items. Operationally, this encourages flatter and more stable packings when multiple feasible packings exist. The assignment constraint ensures that every item is packed exactly once. If you violate this, you either lose items or you pack an item more than once, which is physically impossible. This constraint also provides a clean accounting link between items and bins, so later constraints can rely on the assignment decision to decide whether geometry constraints are active. The bin activation constraint links item assignment to bin usage. If an item is assigned to a bin, that bin must be counted as used. This matters because it prevents unrealistic solutions where items appear in a bin that the model claims is not used. It also ensures the objective correctly counts every bin that contains at least one item. Non-overlap constraints prevent any 2 items from occupying the same physical space in the same bin. For each pair of items, the model enforces that at least one axis separates them. Operationally, this is the core geometric feasibility rule. The big M terms ensure these constraints only matter when both items are assigned to the same bin. Boundary constraints ensure that every item stays inside the bin. Along each axis, the item position plus its size must not exceed the bin size. This prevents placements that stick out of the container. In practice, boundary constraints are essential for safety, handling feasibility, and ensuring the final packed solution can actually be executed. This figure visualizes the mathematical model. You can think of each item as a box with a three-dimensional footprint, and the constraints ensure boxes do not overlap and remain within the bin. A key takeaway is that the formulation is complete but heavy. It is powerful for small instances, but as the number of items grows, we need heuristic and learning-based tiers to scale. This slide gives a concrete example with 3 items packed into one bin of size 10 by 8 by 6. The items have dimensions 3 by 2 by 2, 4 by 3 by 3, and 2 by 4 by 2. One optimal placement puts the first item at 0, 0, 0, the second at 3, 0, 0, and the third at 7, 0, 0. This achieves 100% utilization with total packed volume 36 cubic units. Tier 2 uses iterated local search with perturbation. Local search tries small moves that improve packing quality, such as swapping item order, repositioning one item, or reinserting an item. When the search stops improving, perturbation deliberately changes the solution to escape the local optimum. This is important because packing landscapes have many traps where simple improvements cannot progress. This figure shows the iterated local search loop. You start with an initial packing, repeatedly apply local improvements, and monitor whether you are still improving. If improvement stalls, you apply a perturbation, then continue local search. This combination is often effective because it balances exploitation of good regions with occasional exploration of new regions. In this part, the code makes the slide method executable. Key functions in this chunk include iterated local search 3D packing. You will notice logic related to iteration, objective. As you read it, track what is computed, what is stored, and what gets updated each iteration. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to run this section on a tiny test case and confirm intermediate values before scaling up. In this part, we move from the idea to the mechanics of the implementation. Key functions in this chunk include local search phase and perturbation phase. You will notice logic related to objective. As you read it, focus on the sequence of steps and which variables are carried forward, because that is where most implementation bugs hide. Also check stopping rules and guardrails, so iterative logic stays stable and does not drift. If feasibility is enforced with penalties or repair steps, confirm the penalty scale is large enough to prevent invalid outputs from looking attractive. A practical check is to validate this chunk against a small hand-computed example so you can trust it before using it in production. In this part, the code makes the slide method executable. As you read it, follow the data flow from inputs to outputs and pay attention to how the state is updated. A practical check is to run this section on a tiny test case and confirm intermediate values before scaling up. In the example, the algorithm starts from a greedy bottom-left placement that achieves 85% utilization. A local improvement, such as a 2-opt swap, increases utilization to 92%. After 15 iterations without improvement, a perturbation relocates one item. That disruption opens a new path for local search and allows reaching the optimal 100% utilization solution. Tier 3 introduces the BAT algorithm. Each BAT represents a candidate packing solution, and the search uses a mixture of global exploration and local refinement. Frequency modulation changes the scale of moves, while adaptive loudness and pulse rate decide when to exploit a promising region or explore new configurations. This is useful for rugged solution landscapes like three-dimensional packing. This figure summarizes the BAT algorithm flow and how echolocation-inspired behavior guides search. Conceptually, bats adjust their behavior based on the feedback they receive from solution quality. Over time, the search should shift from broad exploration to focused refinement, which is why adaptive parameters are central to the method. In this part, we move from the idea to the mechanics of the implementation. The key class visible here is the BAT3D packing class. Key functions in this chunk include initializer and echolocation search. You will notice logic related to fitness, population. As you read it, follow the data flow from inputs to outputs, and pay attention to how the state is updated. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. If arrays or tables are involved, double-check indexing and alignment, because off-by-one mistakes are common in time and sequence code. A practical check is to run this section on a tiny test case and confirm intermediate values before scaling up. In this part, you can see the implementation details in action. You will notice logic related to fitness. As you read it, track what is computed, what is stored, and what gets updated each iteration. Also check stopping rules and guardrails, so iterative logic stays stable and does not drift. If arrays or tables are involved, double-check indexing and alignment, because off-by-one mistakes are common in time and sequence code. A practical check is to run this section on a tiny test case and confirm intermediate values before scaling up. In this part, we move from the idea to the mechanics of the implementation. Key functions in this chunk include local search. This part is especially about exploration control. As you read it, follow the data flow from inputs to outputs, and pay attention to how the state is updated. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. If feasibility is enforced with penalties or repair steps, confirm the penalty scale is large enough to prevent invalid outputs from looking attractive. A practical check is to validate this chunk against a small hand-computed example so you can trust it before using it in production. In the reported 50-item example, the method starts with 20 bats and random solutions averaging 68% bin utilization. After 200 iterations, the search finds a solution at 89% utilization, and adaptive parameter tuning supports further improvement to 94% utilization, with 15% fewer bins than the initial greedy baseline. Tier 4 uses meta-learning, meaning the system learns how to choose and tune packing strategies across many different instances. A meta-learner observes features like item size distribution, bin geometry, and constraints, and selects a base algorithm that fits the scenario. This reduces the need for manual trial and error tuning. This figure shows the meta-learning architecture. The meta-learner operates above the base learners and decides which method to apply for a given instance. In practice, this can switch between fast, greedy approaches, more thorough meta-heuristics, or specialized policies for constrained scenarios like fragile or weight-limited items. In this part, the code makes the slide method executable. The key class visible here is the meta-learner 3D packing class. Key functions in this chunk include initializer and extract problem features. As you read it, track what is computed, what is stored, and what gets updated each iteration. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to print or log a few intermediate quantities so you can verify that the update logic behaves as expected. In this part, we move from the idea to the mechanics of the implementation. Key functions in this chunk include forward and meta-solve. As you read it, follow the data flow from inputs to outputs, and pay attention to how the state is updated. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to run this section on a tiny test case and confirm intermediate values before scaling up. In this part, the code makes the slide method executable. Key functions in this chunk include few-shot adaptation. This part is especially about loss computation and gradient updates. As you read it, track what is computed, what is stored, and what gets updated each iteration. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to print or log a few intermediate quantities so you can verify that the update logic behaves as expected. In this part, we move from the idea to the mechanics of the implementation. This part is especially about step-by-step simulation and loss computation. As you read it, focus on the sequence of steps and which variables are carried forward, because that is where most implementation bugs hide. A practical check is to run this section on a tiny test case and confirm intermediate values before scaling up. In the example, the meta-learner is trained on 10,000 diverse instances. When a new electronic scenario arrives with 200 small, high-value items, it selects a modified genetic algorithm automatically. The selected settings include population 150 and mutation rate 0.15. The reported outcome is 91% utilization in 45 seconds, roughly 300% faster than approaches that require manual tuning. Tier 5 moves beyond isolated optimization and introduces a digital twin. A digital twin keeps a live model of warehouse operations, inventory dynamics, and transportation constraints. This matters because packing is not a standalone decision. Real-time signals like equipment status, labor availability, and truck schedules affect which packing strategy is best at that moment. This figure shows the digital twin architecture. The twin synchronizes with systems like warehouse management, tracking, and planning tools, and uses those signals to update packing policies. The main idea is to optimize for the whole system, not just bin utilization. Sometimes a slightly lower utilization can be better if it reduces handling or prevents downstream delays. The digital twin also enables what-if analysis. You can simulate disruptions like equipment failures, labor shortages, and demand spikes. For example, a 30% increase in small electronics orders can change the bottleneck from packing to sorting. The twin reveals where capacity must be added and which packing algorithm should be adjusted for denser, smaller items. In the reported case, a fulfillment center runs a digital twin for 50,000 daily shipments. The system reserves larger containers when popular items arrive in bulk, and it adjusts packing policies to reduce split shipments. The reported results are an 18% reduction in shipping containers and a 25% improvement in order processing time, which translates to about $2.3 million in annual transportation savings. Tier 9 introduces quantum optimization. The idea is to transform the packing problem into a quadratic binary formulation that a quantum annular can handle. Instead of searching sequentially, a quantum annular can explore many configurations through quantum effects. The formulation uses binary variables to represent discretized item, bin, and position choices. This slide shows the quadratic binary objective form. The coefficients encode both the objective and embedded penalties. The success of the approach depends on how well you encode the real constraints into penalty weights, and how finely you discretize the three-dimensional grid. This slide summarizes the penalty structure used in the quadratic binary formulation. Assignment penalties enforce that each item is placed exactly once. Overlap penalties discourage selecting two conflicting placements. Boundary penalties discourage selecting placements outside the bin limits. Together, these penalties push the solution toward feasibility, while the objective still prefers fewer bins and better packing patterns. This figure illustrates the quantum circuit or hardware mapping used for the three-dimensional packing quadratic binary formulation. In practice, a hybrid approach is often used. Classical preprocessing builds the formulation and decomposes the problem. Quantum annealing searches and classical post-processing refines and validates the packing. In the example, a 1,000-item instance is encoded using about 15,000 qubits on a D-Wave Advantage system. Quantum annealing completes in 20 microseconds. After about 8 seconds of classical post-processing, the reported solution achieves 97% utilization, which is 15% better than the best classical method that required about 18 hours of computation. Tier 11 is a future-looking idea: programmable matter. Instead of packing fixed geometry objects into rigid containers, items and packaging could dynamically change shape during packing. This would eliminate many traditional packing constraints. Self-assembly rules and local interactions could produce globally dense packings, while still preserving functional integrity when the items reconfigure back for use. This figure visualizes programmable matter transformation. The key concept is that materials can compress, flow, or reshape during packing and then return to required shapes after delivery. If feasible, this would change packing from an optimization of static boxes to a coordinated physical cyber system that adapts geometry in real time. In the example, an automotive parts distributor moves from managing 50,000 unique stock-keeping units to keeping programmable matter stocks. Items are formed on demand, and packing density improves. The reported space utilization improves from 67% to 94%, inventory carrying costs drop by 78%, and a complex 500-item shipment self-organizes in 12 seconds instead of 45 minutes. These practice questions help you apply each tier. In Tier 1, you build the full mixed integer model and compute a small case by hand. In Tier 2, you design a neighborhood and run a few iterated local search iterations. In Tier 3, you define BAT algorithm parameters and simulate updates. In Tier 4, you design a meta-learning selector. In Tier 5, you design data flows for a digital twin under disruptions. In Tier 9, you build a quadratic binary formulation and estimate qubits. In Tier 11, you design programmable matter transformation rules and estimate space savings. The core lesson is that three-dimensional packing is both a geometry problem and an operations problem. The mathematical formulation gives a complete baseline, but scalable performance usually requires heuristics, meta-heuristics, and learning. As the system context becomes more complex, digital twins help coordinate packing with operations, and frontier ideas like quantum optimization and programmable matter show how the future may shift the computational and physical constraints.